Hi, Marieke. My name's Dana, and I'm on the Ascension team. Sorry I was a bit late. I I just got here, but feel free to try sharing your screen if you can. Um, get started shortly.
Do you know where I share my screen?
Yeah. So at the bottom beside the microphone, there should be this screen icon with a slash, and then if you click it, it should allow you. Yeah. Perfect. I can see something. The Inception.
Okay, I have a lot of windows open, so.
No worries. Amazing. Okay. Maybe we'll just wait a little bit longer. I think some people might be coming from the expo or networking, and then we can get started.
Sounds good.
Right. I still see some people rolling in. So as you're coming in, I guess just a note, if you have any questions, you can put them in the chat and we'll answer them after the session. And we'll get started shortly. I still see the number going up, so maybe we'll wait a little bit longer. Okay, I think we're good to go. So I'll do a quick intro and then the floor will be yours. So hi everyone, welcome to our second speaker series of the day. We hope that you've been enjoying the conference so far, and we're really excited for Dr. Marieke Schmidt. Marieke is an associate professor of earth sciences at Brock University and a geologist who studies igneous and volcanic rocks on both Earth and Mars. She received a BA in geology from Colby College in Maine before going to Oregon State University, where she got a PhD researching the eruptive history and geochemistry of volcanic rocks in the Oregon Cascade Range. She joined the Earth Science Department at Brock University in 2009 and established a research program investigating the eruptive and environmental histories of volcanic fields on Earth and Mars. In late 2020, she was selected by NASA to be a participating scientist on the Mars 2020 Rover mission and will get to work with data from the Perseverance rover. Please welcome Dr. Marieke Schmidt.
Hi, thank you very much. So everyone can see my screen?
Yep, it's good for me.
Okay, so thank you very much for having me today. So the title of my talk is Navigating Mars Rover Datasets. And the goal of this talk is to get you started and thinking about working with Mars Rover datasets. I'll provide you with some background as well as point you towards some links and ways to get started. So you already heard a brief background of who I am, but just to recap, I am a geologist. I started my career working in the Cascade Range on Earth. And then once I finished my PhD, I actually jumped at the chance to get to work at the Smithsonian Institution. I was a postdoc on the Spirit and Opportunity rover, and I've been working with Mars rover missions ever since. When I joined Brock in 2009, since then I've been working with students on both Earth and Mars, primarily focused on the history of volcanic rocks on both planets. And then in 2012, I was selected to be a participating scientist on the Mars Science Laboratory mission. I'm still a participating scientist on that rover mission. And then I recently was selected to be on the Mars 2020 mission, working with the Perseverance rover, and that's been keeping me very busy since then. Okay, I'm also a mom, and this is in part just a warning that because this is the weekend and I'm at home, there might be some kids running in here at some point. So hopefully they'll keep out of it, but I do love to share my love of the natural world and of space with my children. I have a 7-year-old daughter who is absolutely fascinated by rocks and minerals, and she's always has her head down going through gravel pits and things like that. And then my son loves rocket ships and outer space as well, and he's 3. Okay, so the goal of this talk is to get you guys thinking about working with mission data sets. So keep in mind that all missions are publicly funded. So those being NASA, the CSA, or European Space Agency. All mission data is usually eventually made available for everyone's use. So generally, NASA missions hold back their data for approximately 3 months before general release to allow mission scientists a first crack at the results. But after 3 months, those data are available and you can download them and work with them. So students who are interested in working with Mars rover data sets, you might work with other Canadian scientists who are on planetary missions, and there are, we're all over the place. I've just listed some institutions here. There's me at Brock, but there are people working on active missions today at Western, York, Guelph, U of T, McGill, and University of Alberta, and I'm sure I forgot some other institutions. Another option would be to pursue an independent research project, either as an undergraduate student, graduate student, or even later on in your career as an academic or just an amateur. If you're interested, there's nothing holding you back. So how do we get started with planetary data? Well, the first thing you need to be aware of is just what is your personal goal. So do you just want to look at cool pictures? That's certainly fair. There's a lot of great pictures out there. Maybe you want to look for the strange shapes or see if you can find evidence of past life. But there are other reasons why you might want to look at rover data. So you might want to start a business. You might want to develop new technologies or conduct research. So when you get started, the first thing you need to know is the rover payloads and capabilities. And then you need to understand the mission narrative. Okay, so what are the science objectives? Why was the landing site selected? And where are the rovers today? Know the traverse. So where did the rover go and why did it go along that particular path? What are the significant findings? And then also bear in mind that, that there can be wear and tear or loss of instruments over the course of a mission. So for example, a rover mission might lose the use of its abrasion tool, for example, or a brush or something like that that is critical to a certain part of the mission. Sometimes the missions will lose the ability to use a particular instrument. For example, on the Mars Science Laboratory mission, we lost the use of the drill for some time, for almost a year. And then eventually the engineers at JPL were able to develop a workaround, and now that drill is operational again. And then lastly, when you work with planetary data, you're going to want to utilize the mission databases, tools, and published data sets. In particular, I'm going to point you to a couple different locations, one being the Planetary Data System, or PDS, and the other is the Mars Analyst Notebook. So, but first, let's take a step back and think about what the larger narrative is for studying Mars, and that is the big question. And can we find evidence that life occurred outside of the Earth? So, why do we go to Mars? I don't think this will be too big of a surprise for most people logged in here, but basically, we know that life thrives on Earth, and in this plot you can see the mass of the star relative to the sun. So the sun is this very average sized star, and these are the radius of orbit relative to the Earth, and Mars just sits right outside what we think is a potential habitable zone. And the question is whether or not that habitable zone actually does extend to Mars, or if it ever did in the past. And when we look at the two planets side by side, we know that Mars, doesn't have the blue stuff on it. So we don't have, there's no liquid water at the surface today. But also another big difference between the two planets is the size. And the size has implications for what's going on in the planet's interior. So for the Earth, we have an actively churning liquid outer core, and that liquid metal is convecting and it's turbulent, and it's creating the geodynamo that basically has a magnetic shield that is a magnetic field that acts as a shield for solar radiation. And on Mars, the question is whether or not there was ever a liquid outer core in the past. Maybe when Mars was hotter, there was a liquid outer core present. And so maybe there was a shield like this, a magnetic field that protected life in the past. Another big difference between Earth and Mars, of course, is the liquid water on the surface, and this is what's known as a phase diagram for pure water. So what we have is on the y-axis is pressure, and on the x-axis is temperature. And if we look at Earth, the pressure at Earth, it has 1 atmosphere, and we have 3 different forms of water that are stable at the surface. So ice, liquid, and gas are all stable here. And it's just, changed in temperature, and those water will go through those different phase changes. On Mars, the atmospheric pressure is much lower. And so we're actually at this triple point where the atmospheric pressure it's here, and so if you change the temperature, you might go into the ice field or directly into the gas field and skip over this liquid water field. But in the past, we think that that Mars had a thicker atmosphere, and so the atmospheric pressure would have been greater, and the chance that liquid water was once stable is greater as well. Okay, so why do we send rovers to Mars to study habitability? Well, there are other ways to study Mars. The first would be Martian meteorites, and they are awesome. There are a lot of people who study meteorites. We do laboratory analysis for high-resolution studies of mineralogy. We can do radiometric ages of those stones. But the issue with meteorites is that they lack geologic context. And also most are igneous, so they don't give us as much information about past habitability. The Mars orbiters are also awesome. So we have, these provide global scale geomorphology, mineralogy. We can determine the distributions of some elements over the surface. But orbiters are relatively low resolution, and they require some ground truthing to really know what we're looking at. The landers are also great. So I have a picture here from the Viking lander, which was operating on the surface of Mars in 1976. These are relatively low cost and allow detailed experiments. So you can have chemistry, weather, or geophysics conducted at a single location on Mars. And of course, the drawback is that there's no mobility. So in the end, rovers provide a really complementary way to study Mars. They are awesome in another way, and that they are robotic geologists outfitted with scientific instruments that can explore an environment and piece together the rock record to determine past aqueous history and habitability. So what does a geologist do? So I'm a geologist. When I do field work, I get to walk around. So I have a picture of a student just going for a walk around a hillside looking for rocks. We find rocks that we're interested in. We might pick it up and take a close look at it, look at the textures, take notes about it. We'll take pictures. We might use a rock hammer to crack that rock open. We will potentially measure the chemical composition in the field, or else bring it back to the lab and look at it in detail in labs, or with a microscope. So all of these different things all these different strategies are how we do our work on Earth. When you have a robotic geologist, all of it has to be combined. So you have to combine the field capabilities as well as the lab capabilities. Okay. So, and of course, in the eventually we are going to want to send humans to Mars to pick up rocks and then bring them back to labs either on Earth or on spacecraft. Okay, so the different robotic geologists are shown here in this table. There's a lot going on in this table, but there are 4 rover missions that I'm going to talk about in more detail. There's the Mars Pathfinder with the Sojourner rover in 1997. There's the Mars Exploration rovers, which operated starting from 2004, and Spirit could no longer operate past 2009. The Opportunity rover was active on the surface of Mars until 2018. There's the Mars Science Laboratory, or also known as MSL, and this is the Curiosity rover that's been active since 2012. And then finally, the Mars 2020 Perseverance rover, which has been operating on the surface of Mars since February of last year. Okay, so what do all these rovers have in common? They have the ability to get around, so they all have wheels. They're going to have cameras associated with them. So the Pathfinder actually was a combined lander rover mission, where there was a big lander that deployed this little guy. And so the cameras were actually located on the lander itself and not on the rover. But the others all have the ability to take color panorama pictures. From the Mars exploration rovers on, there's also microscopic imager. And then there's recognition that the outer surfaces of rocks of Mars have been, exposed to the Martian environment for an extended period of time. And so for that reason, they'll have weathering rinds on them or coatings of dust. And so these we don't have rock hammers on these rovers. Instead, we use abraders, so to abrade the outer surface of the rock. And so the abrader was present on the Mars exploration rovers. The Mars Science Laboratory actually doesn't have an abrader. It has a brush on it called a dust removal tool, or a DRT. And then the Mars 2020 does have has an abrader, as well as what's called a gas DRT, where it actually puffs nitrogen gas at the surface of rocks to puff out drill fines, abrasion fines, as well as the surface dust. So these two early rovers, Sojourner and Spirit and Opportunity, these guys had instruments on board them, so they could measure the chemistry of the rocks. And these were, in the case of Pathfinder, it was just on the front of the rover. It just rolled up to a rock and measured it. The Spirit and Opportunity rovers have an arm that has instruments on it. The Mars Science Laboratory and Perseverance also have arms on them, but they're much heavier. And so those arms also have drills and sieves and all sorts of other sample processing equipment on them. So they have a much larger, more robust arm. There's other capabilities that have been added over time. So the ability to determine the presence of organics, measure isotopic compositions. There's also the ability to see what's going on in the subsurface. RIMFAX in particular is a ground penetrating radar. And all of these have had weather stations associated with them. I should say there's a weather station on the Mars Pathfinder as well. Okay, so these different rovers, they have different capabilities associated with them, but they also have different mission objectives. So these two earlier missions, Mars Exploration Rovers and Mars Pathfinder, the idea behind those missions was really to follow the water. And it almost became a running joke among the planetary community because we kept finding water on Mars. And that's because there's lots of it present. There's evidence of water in the surface morphology. There's evidence of water in the minerals. If you take a scoop of dirt on Mars, or a scoop of soil, I should say, and heat it up, there's actually water that will come off of it. So there's water that's adsorbed to particles at the surface. Lots of water around. So the next thing that we have to do then, in order to be able to say whether or not there's life, is to find evidence of a habitable environment. So just because water is present doesn't mean that life actually ever thrived there. And then the Mars 2020 mission is to actually find evidence of past life. And so this mission has a very different objective than the previous missions. It actually has a drill on it, and it's collecting samples that will eventually be returned to Earth. So also what goes into building a rover, of course, is that you have to land the rover successfully. And so the Perseverance rover had a really spectacular landing last year. And I'm sure, yeah, it was at a really emotional time, but the engineering feats behind it is not something to scoff at. But what I'm focusing on here for this mission, or for this talk, is going to be the actual operations of the rover on the surface. And this Perseverance rover it represents the first step in Mars sample return. So what is that actually entailing? We are collecting 6 centimeter long samples, basically drill cores into rocks. And this is only this first step of a series of missions that are planned. The first is there's going to be a rover that's deployed called a fetch rover that's going to go and collect those samples and then deliver those to a Mars Ascent vehicle. That Ascent vehicle will launch those samples into orbit to be collected by some orbiter. There is potential for astronauts being involved in this step. And then finally, those samples will be returned to Earth, hopefully by 2034. Okay, so we have all these rovers. Where are they actually located? The first is the Mars Pathfinder. It was sent to Ares Vallis, which was selected on the basis of Viking Orbiter 1 images. And where we had, there's abundant evidence for flood deposits in this region, so flowing water over the surface. Gusev Crater was selected for the Spirit rover, and this was selected because it was thought to be an ancient dried up lake bed. There's this, there's a canyon system that feeds directly into Gusev Crater. And at one time, Gusev Crater did contain a lake and must have, based on these images. Then there was the Meridiani Planum for the Opportunity rover. This site was selected on the basis of mineralogy from orbit. And there was a very strong signal of hematite, which is an iron oxide mineral that forms in the presence of water. Gale Crater was selected on the basis of there being this very large mountain at the center of it, where there's layers that's made up of layered sediments, and the mineralogy in those layers vary according to orbital observations. In particular, there are clay minerals. There's also hematite and sulfate minerals present here. And then lastly, Jezero Crater for the Perseverance rover was selected on the basis of the presence of a delta deposit. So there's this, there's a crater that has a canyon that empties into it, and a platform of sediments around the mouth of that, suggesting that there was standing water present, and that this once hosted a lake. There's also diverse minerals present, including clays and carbonate minerals. There are two other rovers that are either operating or are planned to be operating on the surface of Mars that I'm not going to touch more on. For one, there's the Tianwen-1 Zhurong rover, which is a Chinese rover. It's been operating since last year as well, and it's in Utopia Planitia. There hasn't been much information released about what this rover has found so far. And then lastly, there's the ExoMars rover that is launching later this year. It's set to land in 2023, and that's the Rosalind Franklin rover, and it's planned to go to Oxyaplanum. Okay, so now I'm going to go through the different missions individually and talk about where you can find some information about these missions. So the Mars Pathfinder in Ares Vallis, remember, it was sent to a place where they thought from orbit they could find flood deposits. And in fact, what was found were these angular, sort of jumbled, rocky surface. Not really ideal for finding flood deposits. And when the rover was deployed, it found that the rocks there are actually volcanic in origin, so not sediments or water laid. But they also are relatively rich in silica, and they have an altered surface to them. So this mission was operated for approximately 3 months. The Sojourner rover analyzed chemical composition of about 10 rocks and soils. It found weathered andesitic, basaltic andesitic, it found weathered andesitic and basaltic rocks. And that just refers to the amount of silica present in the rocks. There is a nice overview paper from 1997 if you want to get started on that by Matt Golombek. But if you are interested in actually digging into the data, the best place to start is the PDS, or Planetary Data Systems. I have a site here, but just look up PDS Geoscience Node, and you can find all about the Mars Pathfinder mission there. Okay, so now the Mars Exploration Rover, MER-A. So Spirit is known as MER-A, and it's just known that called that because it was the first rover. Opportunity is MER-B. So when we shorthand them, we call them MER-A or MER-B. So this rover, recall, it was sent to Gusev Crater because they thought they would find evidence of a lake. And what did they find? They found jumbled up, angular, gray rocks. And going up close to it, what did they find? They found that they're actually volcanic rocks. This is a lava flow. It's iron-rich olivine basalt. And here's what the microscopic image looks like. It's about 3 millimeters across. And so early on in the mission, the team decided that the Gusev planes were not going to give the evidence of past water that the team had hoped to see. And so they decided to do a make or break drive to the Columbia Hills. So drive as fast as they could to get there. Bear in mind that this was meant to only be a 90-day or 90 sol mission. And this mission carried on for much longer than that, luckily. So when they first arrived at the Columbia Hills, everything changed. There was abundant evidence of past water there. In particular, there's this outcrop that was found in the Columbia Hills called Home Plate that the rover actually spent quite a bit of time around here. In part because there was an issue with the right front wheel and they couldn't get up steep slopes any longer. And the soils here are very slippery, and the rover ended up getting stuck over on this side, and this is where the rover remains today. But what we found in this region was that there's layered volcanic rock, and it's thought to be formed by explosive magma-water interaction. In particular, there's this feature here that if we blow it up, it actually has this bomb here. It's a larger class that has deformed the underlying strata. And this is a very typical kind of texture or feature that we find in outcrops on Earth, where we have an explosive interaction between water and magma, and this the layered sediment that is deformed must have been saturated with water in order for this to happen. And so here's an example of a place in New Mexico where we see this same sort of feature. So we did find evidence of water here. There's also lots of evidence of alteration at both high and low temperatures. The Mars Exploration Rover Opportunity found a very different kind of environment. It found a sedimentary environment, and there was evidence that sediments were deposited by water, and that water percolated through pores in the sediments. In particular, there are these features that are referred to as blueberries. This is a microscopic image that's 31 millimeters across, and you can see this rounded feature, this sort of weathering out of the rock. And this is a feature that forms when you have water percolating through pores in the rock and then precipitating iron oxide, in this case hematite, around a central seed. And these are common features found in sedimentary rocks on Earth. So here are some hematite concretions found on Earth. Here's another view of this kind of rock. It's layered sedimentary rock, and you can see the blueberries dotted around here. Those are those concretions, hematite concretions. And then there's also this sort of, this kind of, it looks like a knife's gone at it. So these sort of hash marks. And those are interpreted to be crystal casts. If we look at a microscopic imager mosaic, you can see that these are actually places where you can see lenticular crystals have been weathered out. And those are thought to have once been the mineral gypsum, which is a calcium sulfate mineral. And these are also common features in rocks on Earth. So here are crystal casts in rocks on Earth, just for comparison. So we know how these things form in the presence of water near the surface. So how do we find information about the Mars exploration rovers? Well, the planetary data system for the Mars exploration rovers is much more detailed than it is for Mars Pathfinder. There's a very helpful online data repository for these guys. And it takes you to a link where you can get basically all the data for either Spirit or Opportunity for all the different instruments. So APXS, Mossbauer, mini tests, etc. They're all here. All you have to do is not be afraid to click around. Keep in mind what these different shorthanded things represent. RDR is an abbreviation for reduced data records. And so those are going to be the more reduced data. Some of them provide actual oxide abundance data. In other cases, it's just the spectra, which is a little bit less useful depending on how you're planning to use the data. Another place that's really helpful is the Mars Analyst Notebook. Okay, so anybody can access the Mars Analyst Notebook. You do have to create an account, but it's really not a bother to do that. It has a map that is you can navigate through and select which sol you're interested in. So here is a site where the rover ended up, the site 121, and it spent several sols there. So if we're interested in one particular sol, we can see what data were analyzed there, and we can look and see. So has an M highlighted, which stands for microscopic imager. And so if I click that, I can find the image that I'm interested in, and then I can look at the images that way. Okay, but all of the other data are present. You can see this APXS spectra is found there, which gives you the chemical composition for a soil that was measured at this El Dorado dune field. Okay, and so that's what we're seeing here. This is a basaltic sand dune where and you can make out the individual sand grains in this image. And this sort of donut shape is actually because the rover pushed an instrument onto the surface. The Mossbauer was pushed onto the surface, making this imprint on the sands. The last place I'm going to point you to is the Mars Exploration Rover Raw Image Database. This is just another way to easily access the images. So if you go to this site, if we go to the Spirit site, all of the raw images are found here. And you can, select one that's interesting to you. So this is a front HazCam. So it's a hazard camera that's found on the front of the rover. It's all black and white, of course, but you can still get a sense for where the rover was. This is the last HazCam that was actually taken by the Spirit rover, and you can see that it basically got stuck in this very slippery soil. Okay, so now moving on to the Mars Science Laboratory rover Curiosity. This again was sent to the to Gale Crater, and you can see the landing ellipse here. The rover has since left the landing ellipse and has been gradually climbing up Mount Sharp, which is what this mountain is known as. It's a 6-kilometer tall mountain of layered sedimentary rocks. And so here are these sediments. They are dipping away from the crater rim, and they're very fine-grained, which suggests a water-lane deposition. We look up close, you can see that in some of the images, not all, but in some, we see these lenticular crystals that are really sort of reminiscent of what was found in Meridiani Planum by the Opportunity rover. And in fact, these are gypsum crystals in this particular image. We also found, have found and continue to find abundant nodules and concretions in the rock. So you can see these splotches dotted around here. These are like the blueberries found in Meridiani. In addition, there are these light-toned lines that kind of cut across, and what those are veins cutting through the rock. By that I mean that there's cracks in the rocks where fluids have migrated through those and then precipitated minerals. In this case, gypsum, which is that calcium sulfate mineral. And all this comes together and gives a really coherent story that Gale Crater was once the site of a long-lived lake. So what has this rover been doing? It's been really active. It's still actively exploring Mount Sharp. We're on Sol 3,365 today. The rover has driven 27 kilometers, and it's drilled 32 holes into Mars. And so here's a range of the different holes that have been drilled. And you can see that they're pretty variable in color. And that color does reflect differences in the mineralogy that is found. So hematite being more prevalent in the redder ones, magnetite, which is another iron oxide, but with more reduced iron, in the more gray rocks. So just to go through the overall narrative, the rover first landed around here at Bradbury Landing and then drove to Yellowknife Bay, where the rover examined clay-rich mudstones and described its first habitable environment. And then it was decided the rover was just going to take off as quickly as possible over what's known as Bradbury Rise. It passed some alkali-rich sandstones and conglomerates, and then gradually made its way into the lower layers of Mount Sharp, which are called the Murray Formation. And so there's mudstones there. Also, the Stimson Formation, which are sandstones that overlie those mudstones. The rover has been gradually making its way through these mudstones that are laid down in a lake setting. The Bagnall Dunes are these dark-toned or very black sands. They're active basaltic sands that the rover was able to examine. And then gradually it's made its way up, continuing up Mount Sharp. Now it's at, it crossed over the Vera Rubin Ridge, which is hematite-rich mudstones affected by near-surface fluids. Then it went into this region called Glen Torden, would actually drop down a little bit into Glen Torden, which is an area where there's abundant clay-bearing sediments. And then today it's making its way up this clay sulfate transition. So we're anticipating that this rover is going to make its way into sulfate-rich sediments quite soon. And it's climbing, it's also going to climb up on top of this green hue pediment, which is a platform of sediments that formed at the mouth of a large canyon system that's coming down off of Mount Sharp. So a lot has been done on this mission. Where can you explore this mission? Well, there are a lot of ways to do it. NASA provides an interactive map where you can go in and look and see where the rover is and what it's exploring, what it's up to today. There's also this tool, the Explore with Curiosity tool, which allows you to actually follow the traverse and look at mosaics and images, and actually see the rover placed in these locations. It's it's a nice way to spend an evening driving around on Mars. The planetary data system for the Mars Science Laboratory archive is shown here. All of the information about the instruments are located at this site. If you scroll down, if you keep scrolling down from the first page, you're going to be brought to some really useful tools. The first is that MSL Analyst Notebook. It's like the Mars Analyst Notebook for the Mars exploration rovers. It's very similar to that, and so because I already showed you that, I'm not going to show it to you here. But don't be afraid to get the data that way. There's also a link to key MSL science team papers. So basically, there's a running list of all the papers that have been published by the MSL science team here. And so if you want to get started on doing a literature review, that's a good place to go. And then also what is provided is a release schedule. So when is the next round of data going to be released? Remember that I mentioned that the team will hold the data back for about 3 months before it is released to the general public. So the next release date is going to be on March 16th, 2022. Okay, and then lastly, there's this place called the Planetary Image Atlas, and there's a link here. You can get images that way. I haven't found this particular resource to be as user-friendly as some of the others, but you could always find other images here as well. Okay, so lastly, I want to talk about the Mars 2020 Perseverance rover. And this is the landing site in Jezero Crater. Before the rover drove anywhere and made tracks, but there are these blast zones. This is from the sky crane blowing out the surface soil, and you can see the underlying bedrock. The landing site is called the Octavia E. Butler Landing Site, and this is an opportunity where I can point you in towards some really great reading. So Octavia E. Butler is a science fiction author. If you haven't heard of her work, definitely go check it out. I hadn't heard of her before this landing, and now I'm making my way through her books. She writes really interesting science fiction about space travel, the future of human race, but also the intersection with race. And then also, this location has been really interesting because we're making our way to the south here around this particular feature called Sita. Sita is a place that we can't traverse across, but actually the rover has been able to climb down into this particular region and look at the rocks exposed there. Eventually, the rover is going to make its way up onto the delta. We're just not there yet. Of course, there are things that make the Perseverance rover really special and this mission really special. For one, there's the Ingenuity helicopter. So there's some data sets associated with the Ingenuity helicopter that are very cool, including some movies that are fun to scan around and see. So this helicopter was deployed. The helicopter was deployed. Oh no. My system has run out of memory, so hopefully that's okay. Anyway, I'll just carry on. So the helicopter provides some really great data, and the Ingenuity is helping to map out the surface as the rover does its traverse. You can find out where the rover is currently using the interactive map, and so this is where the rover is. It's currently making its way out of the CTAR region, and the helicopter is directly opposite from it. The PDS for the Mars 2020 mission is still getting up and going. Keep in mind that there have only been a couple data releases so far, and the mission took quite a while to start to actually conduct science because it's a very complicated rover. So it took over 90 sols for the rover to actually be doing science operations. And just stay tuned. The first major findings are just now being submitted for publication, so stay tuned. But in the meantime, we are very actively collecting samples. So this is the first sample that was successfully collected. This rock was drilled into, and there's the sample being delivered to the sample tube. So far, we have collected 5 cores, and these cores are being planned to return to Earth by 2034. The samples will be examined in Earth-based labs. So another way to potentially get involved with Mars Rover datasets, is actually to work with the materials that are returned to Earth. Lastly, there's another kind of data that is really cool to this mission, and that is that there are a couple microphones on this rover, and you can actually listen to the rover. So here is the rover actually driving over the surface. There are different ways to, there are lots of different recordings that you can sort of peruse through. It's pretty noisy, isn't it? I'll just end there. So the Mars rover data, just to finalize that, just to end this and conclude it, that Mars rover data are free and accessible. Anyone here can explore Mars. So with that, I'd be happy to take any questions.
Thank you so much. And we do have actually a lot of questions in the chat, so I can read them out to you. The first one is from Jaden. When samples are brought back to Earth, what kind of rock samples would you hope to obtain and why?
Oh, well, I hope there's an echo. Okay.
Oh, is it better now?
I think when you have your sound. Okay. No, still an echo.
Sorry, you're cutting out, I think.
There's an echo. Can you mute, please? Okay.
Can you hear me now?
Can you mute?
Oh.
Thank you. Okay. There's still an echo. Anyway, so I hope that we could collect a diversity of samples, including those that can be radiometrically dated, so we can understand the surface, the age of the surface. But also we want to collect, sorry, this echo is very distracting. Is there any, are people unmuted?
No. Oh.
Okay. It's still an echo. It wasn't there when I was speaking.
Someone in the chat suggested using headphones. I'm not sure if that will help.
I don't have any headphones.
Oh, no worries. I can hear you fine right now, and I can mute myself while you're answering Is it still on your end though, like right now?
I think if you mute, I think no, it's still there. Anyway, I'll just hear this thing going on in my head. Um, so I'm hopeful that we're going to collect samples that are going to be really variable, that are going to be complementary to the meteorites, and hopefully potentially contain evidence of past life. But I don't know what that's going to look like.
Okay, thanks. I had one suggestion, maybe just stop sharing your screen, as I think that screen share is connected to a. Okay. Let's try that. Maybe, hopefully, better.
Is this
okay.
better? No.
No. Oh no. Okay. Well, I guess we'll just try going through the rest of the questions. Because we can hear you on our end.
Okay.
The next question is from Cameron. I may have missed it, but is the data raw or scrubbed for data processing?
Both. So you can get the raw data. You can also get called reduced data records. So ones where they've actually processed the data, and you can get chemical compositions, mineral makeup, as well as like focus merge images. So they're both.
Sorry, Marieke, I think you're cutting out now. We have another suggestion. You may need to mute your computer while you're talking to avoid hearing yourself. I'm not sure if you have a different connection.
Oh, potentially.
Computer, not the mic while talking, if you're able to do that.
Mute my mic?
Mute your computer, not the mic.
Computer. Oh, okay. I can try that, but then I can't hear you. But I can try that. Okay, so you can hear me? Okay.
Can you hear me?
So go ahead and ask a question.
Okay. Would you be able to repeat the answer to Cameron's question? Is the data raw or scrubbed for data processing?
Yes, it is both raw data as well as processed data. So both the raw data are there. You can get raw spectra, you can get raw images, but then you can also get the processed mosaics, focus merge images, things like that as well.
Okay, perfect. The audio is much better now. And the next question is, hello, Dr. Schmidt. It's a pleasure to be hearing your presentation live. I have a question about Martian ice caps. How important it is to study the layered deposits and Martian ice caps in the poles. Can those be a potential site for holding signatures of previous life? I'm quite interested in studying more about it. I'm a fellow geologist as well, and that's from Harsh.
Okay, I think I caught that. The question was about the polar ice caps.
Yeah.
So the ice caps are water. They are, and there's also carbon dioxide there as well. Those ice caps are really interesting because they have a climate record that can be measured. It's not a particularly great place to go for rovers because it can get so cold. There's been the Mars Polar Lander as well as the Phoenix Lander were both sent there. The Polar Lander did not make it, unfortunately. Had a crash landing. The Phoenix Lander was successful, and it didn't actually get those layer deposits, but it did investigate the polar region. And those ice caps are really interesting because they vary through the year, through the Mars year. They also can record the climate history as well. I don't really know much more about that in terms of finding evidence of life there. But it is water, and I remember when Phoenix first found that the water there was a big deal made that they actually found actual water on Mars as opposed to just evidence of it in minerals or from how it's interacted with the surface.
Okay, thank you. And we have another question from Kashfi. Would you know what happens to the rovers or landers that no longer work in the future? Are we going to bring them back?
Unfortunately, we're probably not going to bring them back. They're probably going to stay there for good. The rovers are once they fail to operate, they're just sort of left there. So there's basically spacecraft littered all over the surface of Mars at this point. So there's no plans to bring them back. Maybe they'll be put in a museum or something once humans have actually colonized Mars, but that's about it.
I can't wait for that day. All right, and I think this is our last question, but you had a lot of links in your presentation, and we were wondering if, I think it might be too much work to kind of copy them all into the chat now, but maybe could you send it to Ishan maybe after, and we can kind of distribute those links to the attendees?
Sure.
Okay, perfect. And I don't see any more questions, so I'll quickly wrap up. Thank you so much, Marieke, for your presentation today. I'm sure everyone learned so much. I know I did. I just wanted to tell all the attendees that the 3-minute thesis competition is currently happening now live at the main stage. So I'd encourage you to head over there to check that out. And I think that's it. So again, thank you so much, Marieke, and enjoy the rest of your day.
Thank you.
Thanks.